Okay, so hello and welcome back. So in this video we want to start another chapter of the book class 12. So this is basically class 12, of course NCERT, and this is class 12 part 1, and this is chapter 2 of this book. This is chapter 2 of this book, which is called Inverse Trigonometric Functions. Inverse trigonometric functions. So let's see what we have here. Well, inverse trigonometric functions, of course, are easy, simple, if you know the trigonometric functions, because these are the inverses of trigonometric functions. So to understand this chapter well, you need to understand primarily two things: the trigonometric functions and also the concept of functions. The concept of functions, we have talked about that in well, of course, that you cannot still find on YouTube or anywhere else, but essentially basically we have basically two things here, that we have essentially two chapters here in this whole series of books that deal with functions. If you go to greatitcourses.com, you will see basically a list of all of these class 6, class 7, 8, 9, 10 through 12, and I have basically put all of the class 12 part 1 and part 2. I have made just one class 12 out of that. I don't know why they have made it part 1 and part 2, but it seems logical to me that you can put them together unless there is some problem that they have had, and because of that they have created two parts out of class 12. But for the purposes of what we are doing here, it's just not necessary to make two parts out of that. And if you go to class 11, in class 11 we had relations and functions here, and then on top of that we built basically in class 12 we built also the relations and functions in chapter 1 of class 12 part 1, and but well, all of the videos related to basically chapter 1 class 12 and chapter 2 class 11, everything related to relations and functions, you can already find them on YouTube, and I have done a complete course out of all of these two chapters in one chapter, meaning that I have created a course on YouTube, and then what I have done is that I have created this. As you can see, there is 65 videos here, meaning that actually this is 65 hours of videos. Each of them is approximately 1 hour, so that must be about 65 hours of content here. And if you go in there, there is basically a review of relations and functions. This must be a review. And there's the review over here. Cartesian sets, there is a review here, and there is a review here, there is a review here, there is a review here, and that's it basically. So I have done a couple of videos here, and I have reviewed all of everything that you need to know from chapter 2 of class 11, meaning that all of those things have been covered here. So that's all about functions. Now about about trigonometric functions, I have not done any courses. I mean, I have done courses, but I have not created them for YouTube. If that's necessary, then we will do that as well. But that we will know if that's necessary in the course of creating this video. Moreover, what is important here is that so basically what I'm going to do, I'm going to start with this course. Now, there is basically these two things that you need to do. So first of all, if you have a good understanding of functions, number one, functions. If you have a good understanding of functions, you can of course, that is one of the requirements of this course. And number two, from trigonometry. Right? So trigonometry you need to also understand in order to understand this course. Now, if you don't have a good understanding of functions, you can already, I showed you the playlist on YouTube. You can go there and watch those videos. You have no problem there. If it is necessary for me right now to create some videos of trigonometry, I will do that, and then you will have access to those videos as well, and we are good to go. So these are the two things that you need to understand. Now, if I happen not to do the trigonometry part, hopefully when you're watching these videos, and if you need trigonometry, those videos are also available on YouTube or somewhere else, and then you can go and watch them as well, so that you have a good understanding of inverse trigonometric functions, right? So now let's get started. So first of all, as an introduction, we said that as an introduction of this chapter, we said that basically in chapter 1 of this book, which was about relations and functions, what we basically studied the inverse of a function f. We said that the inverse of a function f is denoted by f inverse, and we said that f inverse exists if f is 1 1 and onto. So we have talked enough about that. It's over 65 hours of videos we have done over there. And now we understand that the inverse of a function f is denoted by f inverse. We know how to find that. We know how to test everything about those functions. And we called that, basically we called the inverse of the function f, we called it f inverse, and we said that f inverse exists if f is 1 1 and onto. We said that 1 1 means basically injective, and we said that onto means surjective, and when both of them are the case in the case of a function, we said that the function is injective and surjective, meaning that the function is bijective. And if the function is bijective, then you can say that f inverse exists, and you can use the methods that we used in the previous course to find it, and you have access to the inverse of a function, right? And you know what it does for you, meaning that, for example, if you have a function like, for example, a function from a set A to a set B, then if you have a function over here, the function f from a set A to set B. So a function is nothing but a mapping from the elements of set A to the elements of set B, having a specific kind of there are specific kind of rules that have to be observed here. If those rules are observed, then you can call that mapping a function. And what it does is that, for example, if there is an x over here, then there is some y over here, and x is under f, x is mapped to y, and we technically say that f of x is equal to y, and that means that y is the image of x under f, or you can say that x is the pre-image of y under f. Meaning that, for example, under some f, for example, you can say that, for example, 2 is mapped to 3, or 3 is mapped to 4, and so on and so forth. So if that is the case, then you can say that, for example, f of 2 is equal to 3, and f of 3 is equal to 4, and so on and so forth, depending on your function. Now, if basically this function is 1, 1, and onto, meaning that if this function is if the image of each and every distinct element in this is your domain of the function, this is the domain and this is the codomain. Now we said that if the image of every distinct element in the domain of the function in the codomain of the function is distinct, meaning that if every element of the codomain of the function is the image of only one of the elements of the domain of the function, then in that case you can say that the function is 1, 1. And what that means is that basically if you have a function like this, for example 1, 2, and 3, and A, B, and C, then if 1 is mapped to A, and if 2 is mapped to B, and 3 is mapped to C under some function f, then you can say that the function is 1, 1. And if basically you have a situation, for example, something like this, where basically, for example, where 1 is mapped to A, 2 is also mapped to A. This would also be a function, meaning that you can say that f of 1 is equal to A, and f of 2 is equal to A also, and so on and so forth. For example, 3, let's say that 3 is mapped to B, and f of 3 is equal to B. But this is not 1, 1, because as you can see, A is the image of more than one element in the domain of the function under f. It's the image of 1, also the image of 2. It has to be the image of only one of these elements here. So it has, and that in that case you would say that f is 1, 1. So that's one of the conditions. The other condition is that this is not allowed, meaning that C must be the image of some element in the domain of the function. If C is left alone, is not the image of some element in the domain of the function, then the function is not onto, it's not surjective, right? Which means that I need to have some element here, 4, for example, which is mapped to C. And then in that case, since every element is covered here, and of course you can imagine that basically this mapping is not there, and of course then I need another element here for 2, meaning that I can put some, for example, some D over here and map 2 to D. And if that is the case where basically every element of the codomain of the function is the image of some element in the domain of the function, then you can say that the function is onto or surjective. Now, if the function is 1, 1, and also onto, meaning that if it is injective and also surjective, then you can call this the function bijective. Then you can call the function bijective, and if the function is bijective, that means that that implies that the inverse of f exists. And the inverse of f exists because, as you can see, under this function f, 1 is mapped to 1, so I can basically make sure that I can do something, basically put together some rule in order to get back from a to 1. Also, there is some way for me to get from 2 to d, and that is the only way that there is to get from 2 to d. I can use the same way or the same route in order to get back to 2 from d, meaning that I can get back from d to 2. I can essentially use the same route to just go back to 2. And as you can see, there is some route from 3 to b, so I can simply use the same, actually I should say route. Some people say route, some people say route, but I suppose route is the right word of pronouncing the word. So I can use the same route to get back from b to 3, right? Again, there is a unique route from 4 to c, so I can use the same thing to get back to 4. That means that, as you can see, there is every possibility that I can get back from the codomain of the function to the domain of the function, and I have no problem there. And so the function is, of course, the inverse of the function can be defined in this case. But suppose that the function is, for example, something like this, 1, 2, 3, 4, and then I have a, b, c, and d over here. Now, suppose that I have the image of 1 is the image of 1 is a, the image of 2 is a, the image of 3 is b, the image of 4 is c, right? Now, well, just ignoring d4 now. Now suppose that now I want to define the inverse of this function and get back from a to wherever I need to go. So if I want to get back from a, I don't know whether I should go to 1 or I should go to 2 or what I should do here. I would get confused, right? So that means that from a, if you want to go back, there are 2 routes to go back along, and so there is no way to know what to do there, and therefore this function is of course not 1, 1. It is not 1, 1, and since it is not 1, 1, then of course the inverse does not exist. But as you can as we saw in the case of this function, from a here there is only one route to go back, so I can go back along the same route and I would have no problems. On the other hand, the same function here, suppose that I want to get back from d to some element, right? In order to basically define the inverse of the function. Now, there is actually no route from anywhere to this element d. So if I were at d, I wouldn't know where to go, right? So, and technically we say that the function is not onto, meaning that this element is left alone here. It's not mapped from any element in the domain of the function. And so now suppose that I start here, I wouldn't know where to go, so I have to stop. And therefore the function, the inverse of the function cannot be defined. There is no way actually to do that. So that is basically the whole concept of functions that we talked about in the previous course. And now one thing that you can do is that sometimes the function is not 1, 1 throughout basically the whole domain of the function, but then if you basically put some restrictions on the domain of the function, then the function becomes 1, 1. And that is the case with almost all trigonometric functions as far as I can tell. For example, sine and cos are such functions, meaning that for example, if you draw the graph of the function, for example, f of x is equal to sine x, you know that sine is a periodic function. It just keeps doing the same thing over and over again from negative infinity all the way up to positive infinity. In some ways, it's the most it is the most boring function I've ever known, and in some ways it's the most helpful and interesting function I've ever known. Up to now, I actually don't know what sort of feeling I have about the sine function, because it just keeps doing the same thing over and over again, and there is really no change in what it does. And but at the same time, it's a value, of course, probably the most valuable function in mathematics, because whatever you want to do, in some way or another, you have to use the sine function. I mean, the whole science of humankind is based on the sine function, really. So, well, if you want to draw the graph of the sine function, so basically you know that sine of 0 is equal to 0, sine of, for example, pi by 2 is equal to 1, sine of pi is equal to 0, sine of 3 pi by 2 is equal to negative 1, and the sine of 2 pi is equal to 0, right? So the function goes from, the function basically keeps doing this over and over again. Just keeps going from 0 to 1 to 0 to negative 1 to 0, and just it keeps doing the same thing over and over again, and in this direction also over and over again, right? Which means that of course the function is not 1, 1. It is onto, there is no problem with that. But the function is not 1, 1, meaning that, for example, you can see that basically over here the value of the output of the function, but actually over here. So if I draw this over here, you can see that the output of the function is going to be right over here, right? So now you can see that, so this is 0, this is pi by 2, this is 0, this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, this is 2 pi, and then what happens if you add pi by 2 to 2 pi? So 2 pi plus pi by 2 becomes 2 pi plus pi by 2 becomes basically 2, and this is 4 pi plus pi is equal to 5 pi by 2, right? So that's 5 pi by 2. So what happens is that basically you can say that f of x, you can say that f of x is equal to sine x is equal to 1 over here. The output is 1. Over here the output is again 1, right? So meaning that, of course, that's not a good statement. Actually, that doesn't mean anything. So I can say that sine of x1, for example, or which is equal to f of x1, is equal to, for example, 1, and I can say that f of x2, which is equal to sine of x2, is equal to 1. And you can just keep going, because you get on basically infinite points or outputs here that are equal to 1. Now, as you can see here, x1, if I take this as x1, if I take this as x2, so you can see that x1 is equal to pi by 2, and x2 is equal to 5 pi by 2. And which means that basically x1 is not equal to x2. So here I'm saying that f of x1 is equal to f of x2, where x1 is not equal to x2, meaning that f is not 1, 1. F is not 1, 1. Which means that, what that means is that basically in the domain of the function, you have this member of the domain which is pi by 2, and also you have this member of the domain which is 5 pi by 2, and in the range of the function you have all of these values ranging from -1 all the way up to 1, right? So I write only the 1 over here, and there is all kinds of numbers here, and there is also all kinds of numbers here. This is your domain, this is your range. Now here, f of, as you saw over here, f of basically pi by 2 is equal to 1. F of 5 pi by 2 is also equal to 1, right? And there is also countless basically inputs that you can find for which the output of the function is equal to 1. Which means that now, as a function, it's okay. There is no problem with it. Of course, there is countless such points that you can find over here. Now, as a function, it's okay. There is no problem with it. But then you will get to a problem. And the problem is that now, suppose that I want to basically, I want to define the inverse of the function, and I'm at 1, and I want to find the route to go back to some element from which we got to 1, right? Now at 1, I get confused. I don't know where to go. I would find an infinite number of points that have been mapped to 1. And so of course, technically we said that the function is not 1, 1. And so the function is not onto. Is not 1, 1, and so you cannot, basically in this form at least, there is no way to find the inverse of this function. But now suppose that I go from for example, suppose that I basically I consider only this part of the function, meaning that I say that f of x is equal to basically sine x, where x basically is lies between 0 and pi, meaning that x belongs to the set 0 and pi. Now, as you can see in this, of course, here again the function is not 1, 1 because of the fact that basically you can see that, for example, the output over here are again 1. So this wouldn't work either, right? So what I can say is that, for example, I can go for only this part. I can go for only this part, meaning 0 to pi by 2. And from 0 to pi by 2, or you can go from negative pi by 2 to pi by 2. So now if I say that basically f of x is equal to sine of x, and if x belongs to the set, for example, 0 to pi by 2, now in this case, of course, as you can see, the function is 1, 1, and of course the function is onto, because the domain is the set of real numbers, the range is the set of real numbers. And so in this configuration, having this constraint on the domain of the function, now the function is 1, 1 and onto, and therefore the inverse of f now exists, right? So that's basically what we do sometimes. We restrict functions intentionally to some domain where the function is actually 1, 1 and onto, and then using that technique you can find the inverse of the function, and your problem is solved. Meaning that, for example, suppose that you have, for example, some function like f of x is equal to, for example, the absolute value of x. The function would be something like this, or exactly this function. Now this function is, of course, is not 1, 1, it's not onto. It's not 1, 1 and not onto. Because if I say that the codomain is R, you can see all of these elements here which are not the images of any elements in the domain of the function. And moreover, the function is not onto because, for example, at this output, you can see that this x1 and x2 are different, but the output for the 2 points are exactly the same. So in such cases, what you can do is that you can restrict, for example, the domain of the function to some values of x where the function is actually 1, 1, and then find the inverse of the function. Meaning that you can say that, for example, let's say that f of x is equal to, for example, the absolute value of x where x is x greater than or equal to 0, and then using that you would get only this part of the function, and this part of the function is 1, 1. It's still not onto, but then there are other things that you can do for that as well, and you will be able to basically use it for some purpose in some context, to solve some problem, basically. Okay. Now let me take a few minutes rest, and then we will talk about the rest of this chapter. Okay, so basically now there are many functions which are not 1, 1, onto, or both, and hence we cannot talk of their inverses unless, as we said, you do something so that the function becomes 1, 1 and onto. Now as we talked about, of course not here, but as we talked about in class 11 about the trigonometric functions, we said that of course they are not 1, 1, and they are not onto over their natural domains and ranges, of course, and hence their inverses do not exist. So what we will do here is basically we will talk about some restrictions on the domains and ranges of those trigonometric functions, which basically then gives us the possibility that those functions will be invertible, and then we will talk a little bit about their graphs and how to draw the graphs and the different properties and characteristics of those functions and their inverses. And you basically one important thing that you need to take into consideration is that basically these, as I mentioned before, these trigonometric functions and of course their inverses, they play an important, not just important, they are the very basics, the very basis of science and technology. And without, for example, without the trigonometry that we have today, probably, for example, your iPhone would not exist, your satellites would not exist, your TV would not exist, or nothing actually would exist without these. And of course, it's not just the trigonometry, but the trigonometry will play an important role in calculus. So these are basically all very useful and important ideas in mathematics. So now in the next video we will talk a little bit about some basic concepts. And so I will see you in the next video. Thank you.